Hello everyone. In this video, we will learn how to start integrating a rational function when the degree of the numerator is bigger than or equal to the degree of the denominator. So, it doesn't matter what you will use in the next step. This must be the first step. You have to reduce in some way the degree of the numerator to a less than degree of the denominator. So key point here is that, so you start with P over Q, okay? And you know that the degree of P is bigger than equal to degree of Q. We cannot integrate this. What we do, we transfer this to something else. How do we do that? We apply long division for polynomials. If you don't remember what was long division, please check your book. In OpenStax, there is a source that you can go and check and make sure that you understand. What we do is this. So I have P, I put it here, then I have Q, I put it here, and then I start doing long division, and long division goes up to somewhere that the degree of that, which we call remainder, is going to be less than degree of Q. So the degree of remainder is always less than degree of Q. And while you're doing this thing, you get this quotient thing going on there. Okay, so that if you do that step, those long division, then you can rewrite Px over Qx as something nice. It will be this Sx, which is just a polynomial, plus remainder over the same Qx. And since remainder is always less than, has degree less than degree of Q, so this new rational function has degree of the numerator less than degree of the denominator. So if you have been trying to integrate, now you will have an integral of a polynomial and then an integral of another rational function, which this time has degree less than degree of Qx. Well, what can we do with that one? Ultimately, we will learn, but in some examples that I'll show you, this one will turn out to be one of these partial fractions. Okay, so let's do some examples and see. Here, the degree of the numerator is 1, degree of the denominator is 1. These are equal. So what we do is long division. So I start with x plus 5, 3, the Reynolds, sorry. 3x minus 1, p always goes there, q is x plus 5. And then we start here 3 times that, this is 3x plus 15, and then minus, you cancel that, and then here you get negative 16. In this question, remainder is this guy here. This is Rx. Well, it doesn't have any x, it's just constant polynomial, which is good, and this is Sx. So with the long division, what we have shown is that 3x minus 1 over x plus 5 is equal, remember always, Sx, here is 3, plus Rx, which is negative 16, over Qx, which is x plus 5. And since we were looking for integral of that, now we can separate these integrals, and we have integral of a polynomial, just 3, that's 3x, plus, well, I can bring that negative 16 out, and I know that integral of 1 over ax plus b is 1 over a, here is 1, ln of x plus 5, absolute value of that That's what we need. So I first applied long division and generated a new rational function together with a polynomial, but the new rational function has degree of numerator less than degree of the denominator. And then we can integrate. At least in this case, that rational function, the new rational function, is a partial fraction. Okay, let's do one more example here. So here this is p, and its degree of p is 3, and degree of q, which is the denominator, is 2, and it is bigger than. So we have to apply long division. 2x cubed plus 2x squared plus 2x plus 1 divided by x squared plus 1. So we start with the leading terms and always work with leading terms. So what should I multiply to x squared plus 1 so that I get 2x cubed? That would be just 2x. Then I multiply that and write it here. That will give me 2x cubed plus 2x. Then I subtract. While I'm subtracting, I subtract the whole thing. This will cancel with that. Oh, see, this will cancel with that. This was lucky case here. So then I will bring, subtract it, yes. Now, it's time for the second term. Now again, look at the leading terms here. 2x squared, that's x squared. What should I multiply to x squared to get 2x squared? Just 2. Then multiply, you get 2x squared. So you, oops, we already did that term. So now it's time to multiply that. This is 2x squared plus 2. Then subtract from the upper one. This will cancel with that. And there we will get -1. Okay, so what we did was that 2x cubed plus 2x squared plus 2x plus 1 over x squared plus 1. Now this is remainder, and that is the quotient term. So here I will get the polynomial s plus the remainder over the q. Now, if you were integrating, which we were, this will turn into two easy integrals. The first one will give me x squared plus 2x. The second one, you see, 1 over x squared plus 1. This is tan inverse of x plus c. And we are done. One more example. Okay, here again, the degree of the numerator, which is p, is 3, and degree of the denominator, which is x squared plus 2x plus 1, is 2, and that's bigger than that. So you always, in these cases, start with long division. X cubed here, x squared plus 2x plus 2. So leading term is x cubed. What should I multiply to leading term of this guy to get x cubed? I need just one x. So that will be, I'm multiplying this there and writing down there. So x cubed plus 2x squared plus 2x. Subtract, and then this will cancel with that. And then the rest will come just down. Negative 2x squared, negative 2x. Look at the leading term. What should I multiply to leading term of the denominator? Here, x squared, to get the leading term there. So that is negative 2. When we multiply, what do we get? Let me just don't make that mess there. That will be a negative 2x squared, negative 4x, negative 4. And then we want to subtract that, yes. So this will cancel with that. Those two will give me 2x, and that will just give me plus 4. Okay, so here what we did was that we wrote x cubed over x squared plus 2x plus 2 as Sx, x minus 2 plus remainder 2x plus 4 over q. Now we were integrating so we can separate these integrals, and as a result now we have x squared plus 2 minus 2x from the first one. For the second one, now we have to do the integration. So let me just quickly do it here. 2x plus 4 x squared plus 2x plus 2 dx. Remember that we have to generate the derivative. Derivative here is plus 2. So x squared plus 2x plus 2. If you don't know what I'm doing here, please check the previous video. Over there we explain this. So get rid of 2. This will give me ln of x squared plus 2x plus 2. What does this other one give me? Okay, for that we have to do some work. So that will be complete square. And then if we set u to be x plus 1, that will give me integral of 1 over u squared plus 1 du. And that is 2 tan inverse of u plus c, which is 2 tan inverse of x plus 1 plus c. So I can now see that, oh, I can bring this back and put it there. So this will be 2 tan inverse of x plus 1 and then plus c. So we use the long division to long division to reduce that. Now back, I'm taking this whole thing and then plugging it there, plus ln of x squared plus 2x plus 2 plus 2 tan inverse of x plus 1 and then plus c. So first you have to make sure that you, using the long division, make the degree of the numerator less than, and then look at the what you found after that process. Depending on the techniques that we will learn from this point on, you can do the solution, your integrate.